Well, welcome back to our class on algorithms and data structure. We have completed now a couple of the different types of data structures that we wanted to talk about. We've talked about bags, we've talked about stacks, we've talked about queues, and now for this lecture, we're going to be getting into recursion. And so the recursion is a major feature of many algorithms. In fact, repeating actions repeatedly is a key element of computers. Two problem-solving processes involve repetition. They are called iteration and recursion. In fact, most programming languages provide two kinds of repetitive construction constructs, iterative and recursive. You know about iteration because you know how to write a loop, regardless of the loop's construct you use, whether it be for, while, or do. Your loop contains the statements that you want to repeat and a mechanism for controlling the numbers of repetitions. You might have counted a loop that counts repetition as 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1, where the loop might execute repeatedly while the Boolean variable or expression is true. Iteration often provides a straightforward and efficient way to implement a repetitive process. At times, iterative solutions are elusive or hopelessly complex. For some problems, discovering or verifying such a solution is not a simple task. In these cases, recursion can provide an elegant alternative. Some recursive solutions can be the best choice. Some provide insight for finding a better iterative solution, and some should not be used at all because they are grossly inefficient. Recursion, however, remains as important problem-solving strategy, especially in the area of cryptography and image processing. So in this chapter, we will have you get a chance to be thinking about recursive and recursive kind of actions. So here is what we have in terms of the contents for the chapter. We'll give an overview of what recursion is, talk about tracing a recursive method. We'll look at recursive processes in an array, looked in at recursive processing, a linked chain, and the time efficiency of recursive methods. Then we'll finish up with talking about tail recursion and using a stack instead of a recursion. So what is recursion? You can build a house by hiring a contractor. The contractor in turn hires several contractors to complete portions of the house. Each subcontractor might hire other subcontractors to help. You use the same approach when you solve a problem by breaking it into smaller problems and writing methods to solve those problems. In one special variation of this problem-solving process, the smaller problems are identical except for their size. This special process is called recursion. Suppose that you can solve a problem by solving an identical but smaller problem. How would you solve the smaller problem? If you use recursion again, you will need to solve an even smaller problem that is just like the original problem in every other respect. How will replacing a problem with another one ever lead to a solution? One key is the success of recursion is that eventually you will reach a smaller problem whose solution you know because either it is obvious or is given. The solution to the smallest problem is probably not the solution to your original problem, but it can help you reach it. Either just before or just after you solve each smaller problem, you usually contribute a portion of the solution. This portion, together with the solutions to the other smaller problems, provide the solution to the larger problem. So here's just a fun little example. In terms of counting down, you've probably been in an experience where you've been counting down to New Year's Eve and changing into the new year. So it's New Year's Eve and the giant ball is falling in Times Square. The crowd counts down 10, 9, 8, etc. Suppose that I asked you to count down to 1, beginning at some positive integer like 10. You would shout 10, and then your friend would count from 9. Counting down from 9 and counting down from 9 is a problem that is exactly the same as counting down from 10, except that there is less to do. It is a smaller problem. To count down from 9, your friend shouts 9, and ask a friend to count down from 8. The sequence of events continues until eventually some friend is asked to count down from 1. That friend simply shouts 1. No other friend is needed. You can see these events as laid out interestingly in a fun way in this figure. So what does any of this have to do with Java? In the previous example, you play the role of a Java method. The client, the client, have asked you the recursive method to count down from 10. When you ask a friend to help, but you invoke a method to count down from 9, but you do not invoke another method, you invoke yourself. For the method countdown, we have the following answer to these questions. The method countdown displays the given integer as a part of a solution that is contributed directly. This happens to occur first here, but it need not always occur first. The smaller problem is counting down from an integer -1. The method solves a smaller problem when it calls itself recursively. The if statement asks if the process has reached the base case. Here, the base case occurs when integer is 1. Because the method displays integers before checking it, nothing is left to do once the base case is identified. So here's a couple of definitions, things to think about. Recursion is a problem-solving process that breaks a problem into identical but smaller problems. And a method that calls itself as a recursive method. The invocation is a recursive call or recursive invocation. And a couple other things to think about. A recursive method uses more memory than an iterative method in general because each recursive call generates an activation record. And questions to answer here note are some questions to answer when designing a recursive solution. What part of the solution can you contribute directly? What smaller but identical problem has a solution that, when taken with your contribution, provides a solution to the original problem? And when does a process end? That is, when is a smaller but identical problem has a known solution, and have you reached the problem or base case? So these are the kind of things that you want to be thinking about as you're going through working on a problem and designing, having the design guidelines to get to the state you want to go. So in terms of a programming tip, iterative methods contain a loop. Recursive method calls itself, and some iterative methods contain a loop and call themselves. And so in terms of a programming tip for Stack Overflow, a recursive method that makes many recursive calls will place many activation records in the program stack. Too many recursive calls can use all the memory available for the program stack, making it full. As a result, the error message Stack Overflow occurs. Infinite recursion or large size problems are the likely cause of this error. So that's something you want to be aware of and careful of. So let's do a tracing of a recursive method. And this is going to be for the method countdown. So let's trace the method countdown given in segment 9.3. For simplicity, suppose that we invoke the method with a statement countdown 3. From within a main method of the class that defines a countdown, this call behaves like any other call to a non-recursive method. The argument 3 is copied into the parameter integer, and the statements are executed. A line containing 3 is displayed, and the recursive call countdown 2 occurs. You see in the middle of the figure. Execution of the call to countdown 3 is suspended until the result of countdown 2 are known. And so it goes on and on and on. Continuing our trace, countdown 2 causes the following statement shown to execute. A line containing 2 is displayed, and the recursive call countdown 1 occurs as shown in figure 9.2b. Execution of the call to countdown 2 is suspended until the results of countdown 1 are known. The call countdown 1 causes the following statements to be executed, and a line containing 1 is displayed as shown in figure 9.2c, and no other recursion calls occur. This method complete execution and returns to the client. So that's finishing up on this previous figure. And now in this figure, figure 9.3 illustrates a sequence of events from the time that countdown is first called with argument 3. The number arrow indicates the order of the recursive calls and the return from the method. After 1 is displayed, the method completes executions and then returns to the point arrow 4. After the call down 2 minus 1, execution continues from there, and the method returns to the point arrow 5, and after the call countdown 3 minus 1, ultimately the return to the point arrow 6 after the initial recurrence calls in the main occurs. And so we can see it goes down and it goes back up. So figure 9.3 appears to show multiple copies of the method countdown. In reality, however, multiple copies do not exist, except for each call to the method, be it recursive or not. Java records the current states of the method's execution, including the values of its parameters and local variables, as well as the location of the current instruction, as segment 522 of chapter 5 described. Each record is called an activation record and provides a snapshot of the method state during its execution. The records are placed into the program stack. The stack organizes the records chronologically so that the records of the currently executing method is on top. In this way, Java can suspend the execution of a recursive method and invoke it again with new argument values. The box in figure 9.3 corresponds roughly to activation records, although the figure does not show them in the order in which they would appear in a stack. Figure 9.4 illustrates a stack of activation records as a result of the call countdown 3 in a main method. So we're just getting some more details about how all of this is working, the stack of activation records. Moving on, here we're seeing an illustration of the stack of activation records during the execution of the call countdown 3. So let's talk about recursive methods that return a value. The recursive method countdown in the previous section is a void method. Value methods can also be recursive. The guidelines for successful recursion given in segment 9.4 applies to a value method as well, with an additional note. Recall that a recursive method must contain a statement such as an if that chooses among several cases. Some of these cases lead to a recursive call, but at least one case has no recursive call. For a valued method, each of these cases must provide a value for the method to return. The definition of the method sum of satisfies the design guidelines for successive recursion. Therefore, you should be confident that a method will work correctly without tracing its execution. However, a trace will be instructive here because it will not only show you how a valued recursive method works, but also demonstrate actions that occur after a recursive call is complete. Suppose we invoke the method with the statement system output print ln sum of 3. The computation occurs as follows. Sum of 3 is sum of 2 plus 3. Sum of 3 suspends execution and sum of 2 begins. Sum of 2 is sum of 1 plus 2. Sum of 2 suspends execution and sum of 1 begins. Sum of 1 returns 1. Once the base case is reached, the suspended execution resumes, beginning with the most recent. Sum of 2 returns 1 plus 2 or 3. Then sum of 3 returns 3 plus 3 or 6. And then figure 9.5 illustrates this computation. So what about recursively processing array? Later in this course, we'll talk about searching an array for a particular item. We'll also look at algorithms that sort or arrange the items in an array into either ascending or descending order. Some of the more powerful searching and sorting algorithms often are stated recursively. In this section, we will provide an array. We will process arrays recursively in ways that will be useful to us later. We have chosen a simple task displaying the integers in an array for our example so that you can focus on the recursion without the distraction of the task. You'll consider more complex tasks later in this book and in the exercise at the end of the chapter. So let's start with the array first. So an iterative solution often starts at the first element array first. So it is natural to have your first recursive method begin there also. If I ask you to display the array, you could display the integer in an array first and then ask a friend to display the rest of the array. Displaying the rest of the array is a smaller problem than displaying the entire array. You wouldn't have to ask a friend for help if you had to display only one integer. That is, if first and last were equal. This is the base case. Thus, we could write the method display array as we're showing in the chart. Now, how about starting with array last? Strange as it may seem, we can begin with the last element in the array and still display the array from its beginning. Rather than displaying the last integer right away, you would ask a friend to display the rest of the array after the integers in the array first through array last minus 1 had been displayed. You would display the integer in array last. The resulting output would be the same as a previous segment. The method that implements this plan is shown here in the figure. So in this figure, we show two arrays and the middle element. Suppose that we include array mid in the left half of the array, as shown as the figure shows. In part A, the two pieces of the array are equal in length. In part B, they are not. This slight difference in length doesn't matter. So we divide the array in half. A common way to process an array recursively divides the array into two pieces. You then process each of the pieces separately. Since each of these pieces is an array that is smaller than the original array, each defines a smaller problem necessary for recursion. For our first two examples, also divide the array into two pieces, but one of the pieces contains only one element. Here we divide the array into two approximately equal pieces. To divide an array, we find the element at or near the middle of the array. The index of the element is t mid equals first plus last divided by 2. So think about displaying a bag. In chapter 2, we used an array to implement the ADT bag. So suppose that the class array bag had a method displayed to display a bag's contents. Although we could define this method iteratively, we'll use recursion instead. Since the method display has no parameters, it must call another method display array that has parameters and displays the array of bag entries. The arguments in the call to display arrow would be 0 for the first index and number of entries minus 1 for the last index, where number of entries is a data field of the bag's class. Since the array bag of entries is a data field of the class that implements the bag, it needs not be a parameter of display array. Because display array must have specific data via its parameters about the array of bag entries, it must be private. Finally, since display is not a static method, display array is not static. We can use this approach of any version of display array given previously. However, we will display objects one per line instead of integers on one line. Using this technique shown in segment 916, we revise the method as listed here in the chart. Okay, what about recursively processing a linked chain? We can illustrate the recursive process of a chain of linked nodes by performing a simple task such as displaying the data in the chain. Once again, we'll implement the method display for the ADT bag, but this time let's use the linked implementation introduced in chapter 3. That implementation defines a field first node as a first reference to the first node in the chain. Dividing a linked chain into pieces is not as easy as dividing an array, since we can't access any particular node without traversing the chain from its beginning. Hence, our first approach displays the data in the first node and then recursively displays the data in the rest of the chain. Thus, as we did in segment 919, display will call a private recursive method. We will name that method display chain. As a recursive method, display chain needs an input value. That input should represent the chain. So we give display chain a parameter that references the first node in the chain. Suppose that we name display chain's parameters node 1. Then node 1 dot get data is the data in the first node, and the the node 1 dot get next node is a reference to the rest of the chain. What about the base case? Although one element array was a fine base case for a display array, using an empty chain as the base case is easier here because we can simply compare node 1 to null. Then we have the following implementation for the method display and display chain. Okay, let's talk about displaying a chain backwards. So suppose that you want to traverse a chain of the linked nodes in reverse order. In particular, suppose that you want to display the objects in the last node, then the one in the next to the last node, and so on, working your way towards the beginning of the chain. Since each node references the next node, but not the previous one, using iteration for this task would be difficult. You could traverse to the last node, display its contents, go back to the beginning, and traverse to the next to the last node, and so on. Clearly, however, this is a tedious and time-consuming approach. Alternatively, you could traverse the chain once and save a reference to each node. You could then use these references to display the objects in the chain's node in reverse order. A recursive solution would do this for you. If a friend could display in reverse order the nodes of the subchain that begins with the second node, you could display the first node and complete the task. And so the following recursive solution implements this idea, as we can see in this chart. Well, let's talk about the time efficiency of recursive methods. Chapter 4 shows you how to measure an algorithm's time requirements by using big O notation. We used a count of the algorithm's major operations as a first step in selecting an appropriate growth rate function. For the iterative examples we examined, that process was straightforward. We will use a more formal technique here to measure the time requirement of a recursive algorithm and thereby choose the right growth rate function. So for the time efficiency of countdown, as a first example, consider the countdown method given in segment 9.3. The size of the problem of counting down to 1 from a given integer is directly related to the size of that integer. Since chapter 4 used n to represent the size of the problem, we can change the name of the parameter integer in countdown to n to simplify our discussion. Here is the revised method that we're showing in the chart. So we can compute x to the n for some real integer x in an integral power n greater than or equal to 0 more efficiently than the approach that question 8 suggests. That if you can look in the text for that, to reduce the number of recursive calls and therefore the number of multiplications we can express. You can see some of the manipulations that were shown in the chart. The computation could be implemented by a method power xn that contains a recursive call power comma n over 2. Since integer division in Java truncates its result, this call is appropriate regardless of whether it is n is even or odd. Thus, power xn would invoke power x n over 2 once square the result, and if n is odd, multiply the squared by x. These multiplications are big O notation 1 operations. Thus, the execution time for power xn is proportional to the number of recursive calls. The recursive recurrence relationship that represents the number of recursive calls and therefore the method's time required to compute. So continuing on, let's talk about tail recursion. Tail recursion occurs when the last action performed by a recursive method is a recursive call. For example, the recursive method countdown from segment 9.6, which is a tail recursive. The tail recursion is a method that simply repeats the method's logic with changes to parameters and variables. Thus, you can perform the same repetition by using iteration. Converting a tail recursive method to an iterative one is usually a straightforward process. For example, let's see how to convert the recursive method countdown just given. First, we replace the if statement with a while statement, then instead of the recursive call, we assign its argument integer -1 to the method's parameter integer. Doing so gives us the following iterative version of the method that we're showing there and the bottom of the chart. The method is essentially the same as the iterative method given in segment 9.7, because converting tail recursions to iteration is often complicated. Some languages other than Java automatically convert tail recursive methods to iterative methods to save the overhead involved with recursion. Most of this overhead involves memory, not time. If you need to save space, you should consider replacing tail recursion with iteration. So what about using a stack instead of recursion? One way to replace recursion with iteration is to simulate the program stack. In fact, we can implement a recursive algorithm by using a stack instead of recursion. As an example of converting a recursive method to an iterative one, we will consider the method display array as given in segment 9.18. For this demonstration, we will reverse display array to be non-static method in a class that has an array as the data field. Okay, just to finish up here, so using stack instead of recursion, in general, when a method begins execution, it pushes an activation record onto the program stack. As it returns, a record is popped from the stack. We want an iterative display array to maintain its own stack. When the method begins execution, it should push a record onto the stack. Each recursive call should do likewise, as long as the stack is not empty. The method should remove a record from the stack and act accordingly to the contents of the record. The method ends its execution when the stack becomes empty. This approach does not always produce an elegant solution. We certainly could write an iterative version of display array that was easier to understand than the version and did not require a stack, but sometimes a simple iterative solution is not apparent. In such cases, the stack approach offers a possible solution. We will see more useful examples of stack-based iteration in chapter 25. Okay, that's for this lecture. Thank you very much.